Hello students, this is Mr. Morgan and here's video 5, equation building and mathematical operators. And hopefully by the end of this video you're going to learn how mathematical operators affect the meaning and value of variables in equations, and we're going to learn how to build equations and use them to accomplish our goals in physics. The word equations often make you think of some complex set of symbols and maybe some numbers and constants that when you throw some numbers into one side of it, it spits out some numbers on the other side. And that's kind of disappointing because what physics equations are supposed to be are beautiful and elegant solutions to explain natural phenomena. And I'm hoping that if we approach equations correctly in this class, you'll get to see them that way. So one of the things that we're going to do is we're going to have you sort of discover your own equations. And by discovering them yourself, you will understand why they work the way they do, why they fit your observations. And if we do it that way, it'll allow you to do things like predict the future and explain the past when looking at specific relationships. So we're going to look at equations that have all kinds of effects, and we're going to learn how to make equations that can act like a pendulum, or look at the force of a spring, the motion of a car, or even predict the motion of a planet. We're going to try to figure out what variables control the behavior of specific objects, and we're going to look at the relationships of objects in compared to each other, and whether that, when we draw the line of best fit, is that a linear, inverse, or some other type of relationship that we haven't discussed yet. And eventually we can take lots of relationships and compound them together into simple and more complex equations as we get better at physics. And so hopefully this will be a fun little journey that we take together. So let's imagine a relationship between two things in the real world: teacher niceness and candy given out. And we'll plot the data on the graph that you see before you and draw a line of best fit. And we can notice a couple of things. We have a straight line, which means this is a linear relationship. And we also notice that candy, if we graph it on the x-axis, it's going to be our independent variable. And that niceness, if we graph it on the y-axis, is going to be our dependent variable, and it's going to depend upon how much candy that teacher gives out. So let's dive a little bit deeper. Let's look at how you build an equation that reflects a linear relationship. We're going to start with our dependent variable, and we're going to put it on one side of the equal sign. Then any independent variables within the linear relationship will go on the other side of the equation, and we're going to make sure that they're in the numerator position, so they're on top if there's division. And it's going to look like this. So here we have niceness of the teacher is equal to candy given out by the teacher plus some other factor. So then we have to ask the question, well, why does this work? Well, niceness has to be equal to or proportional to candy. Both of these sides of the equation have to be equal when we're done, so that if you increase candy, niceness also has to increase. So in the end, it makes a nice line. But let's imagine there are more variables that have to do with teacher niceness. Teacher niceness might also depend on how much homework that teacher assigns. Where as the amount of homework increases, we imagine that teacher niceness goes down and down and down. In this case, niceness is still the dependent variable, and it depends on the amount of homework given. And you might remember that this is an inverse relationship, so as we grow one variable, the other variable shrinks. So how do you build an equation that reflects an inverse relationship? We're going to build it the same way we built the linear relationship. We're going to start with our dependent variable, which is teacher niceness, and we're going to put it on one side of the equal sign. Our next step is to take our independent variable with an inverse relationship, the amount of homework given, and we're going to put it in the denominator position on the other side of our equal sign. And it looks like this, where niceness equals 1 over homework given. And it works because as we increase homework in this equation, it creates a fraction that gets smaller and smaller. And niceness has to shrink in order for our equation to remain balanced. So if I crossed out h and I put in a value for homework of, let's say, 5, we can see that our niceness is going to be equal to 1/5 of what it was if our homework was equal to 1. So when you feel like you've identified all of the relevant variables in a relationship, we can put them together to make a single unified equation. We're going to leave the dependent variable niceness alone on one side of the equation. And for our two independent variables, well, we just multiply them together on the other side of the expression. And it looks a little something like this, where niceness is left alone is going to be equal to the amount of candy given out multiplied by 1 over the amount of homework given. So if you want to simplify it and you are confident that there are no other relevant relationships in teacher niceness, you've finished and you now have created this beautiful equation. Niceness is equal to the amount of candy given out and divided by the amount of homework given. You own this relationship, it belongs to you, and you can be confident that you can accurately gauge how nice teachers are, and that if a teacher gives out double candy, they're double nice, and if they are giving out double homework, then they are half as nice. So there you go. So let's test our equation. And if an equation is working properly, it should behave predictably. So what we're going to do is we're going to hold one variable constant. And in this case, we're going to keep the amount of homework that the teacher assigns constant. And we're going to play with how much candy they give out to test the dependability of our equation. So let's look. If I give out 6 pieces of candy for the 2 pieces of homework, we should expect to get 3 niceness on our teacher scale. If I double the amount of candy, then we should double the niceness. And if I give you 1/3 the candy and the homework remains the same, then we should also expect to have 1/3 the amount of niceness. So that's one way to test our equation. So there's another test we can do because we have one more independent variable. And in this case, we're going to hold our amount of candy constant, and we are going to change the amount of homework that's given out. So if I have 2 pieces of candy given out and 6 pieces of homework, we can expect our teacher niceness factor to be 1/3. If I double the amount of homework, then my niceness is going to be half of what it was before, 1/6. And then if we decrease the amount of homework to 2, our niceness will increase to 1. So there we have it. We have made an equation that captures both relationships and lets you predict how nice any teacher will be if you can measure out the candy and homework that they give out. So as we go on to build more and more equations that describe more and more physicsy things, we're going to need to know more and more symbols, and these symbols are called mathematical operators, and some of them you're already familiar with. They're shortcuts that tell you what to do with the following value or the number that comes after it. And we have some familiar ones. There's the addition symbol, there's the subtraction symbol, the square root, the less than or equal to, and the next set of variables I show you are going to work in the same way. And if you like to, you can write down what they mean so that when you see them in equations, um, or if you're building your own equation to describe something, you'll have those in your toolkit. So I'm going to give you some new operators to look out for as we do more physicsy things. Subscripts. So we're going to use subscripts in physics to clarify when we have two similar variables, such as two velocities or two distances or two forces. And examples of how those work might be the use of the initial and final subscripts. We use these a lot where we want to describe the distance at 2 points in time. So we'll have di, which means the starting distance from two different objects, and df or d final as the final distance or the ending distance displacement between two objects. Some other subscripts that we use if we're using multiple velocities in an equation, we might want to distinguish the dog's velocity from the cat's velocity. Or if we have multiple forces going on, we might want to distinguish gravitational force from a pushing force or the pulling force, normal force, anything like that. Another symbol or mathematical operator that we use is the delta symbol, and this indicates a change in a variable. If you see delta before a variable, you just want to know how much that variable has changed, and we can calculate that by taking the final value and subtracting it from the initial value, or sometimes you'll add up all the incremental changes that you see along the way. So an example would be that if we start at 2 minutes and then we finish at 9 minutes, then our change in time is 7 minutes. And then for delta d, if the initial distance is minus 40 and the final distance is minus 50, then our change in distance is negative 10 meters. Average, AVG. This is a subscript that stands for average. If a variable has a subscript AVG, then it means that it wants you to find the average. So you're going to add up all the initial and final values and then divide them by the number of values you added together. Think about what would be right in the middle of all the values that you've recorded. If the initial distance is negative 40 and the final distance is negative 50, then that average is going to be negative 45, just as an example. The next mathematical operator that I'll be using is the sigma, and this means to add it all up. So if a variable has a sigma in front of it, you should find the sum or total of all the values. So as an example, if 3 of your friends have $10 each and you have $5, the sum of your money is $35. So in closing, we can look at an equation as something that can be built out of one or even more relationships. Equations are shortcuts that let you predict the future and calculate values more efficiently. You can also reverse the process and use an equation to help you explain the relationships that impact a single variable. You should pay close attention to math operators. They can totally change the meaning and the value of a variable. So look out for those subscripts and pay attention to what they do. If you have any more questions, come find me during class or during tutor time, and I can help you out with this crazy math stuff. But I hope you enjoyed the presentation.